Okay. All right. The Valles Marineris, that's the Great Mariner Valley of the planet Mars. It's the largest valley network in our solar system. In fact, on Earth, it would extend right across the entire USA from coast to coast. And it's an enigma still today. How did such an enormous valley network form in the first place? We know that once it was established, it was scoured and over-deepened by what we know were likely to be flash floods of water that emptied out onto the northern plains. Let's go to the next slide, please, Chris. Onto the northern plains at the eastern end of the Mariner Valley system. There's the Mariner Valley, and this is the end where we know that water flushed out and into the northern plains, which are all essentially most of the northern hemisphere. But there remains much debate over how the valley network was initiated in the first place. Now, one potentially important clue is provided by its location, and it lies due east of the Tharsis Plateau. That's this entire area here. And these three major volcanoes, then of course there's Olympus volcano just over the horizon there. Next one, please. Good. Now, more clues come from the European Space Agency, who released an outstanding high-resolution image. It's a high-resolution 3D perspective natural color image, which was taken by the Mars Express satellite back in 2009. And it illustrates a very small segment of the Mariner Valley network, known as Hebe's Chasma, which I presented to you, actually, in early 2010. Next one, please, Chris. Now, Hebe's Chasma is clearly closed at both ends. Here's the chasma seen in an older picture, but look, it clearly is closed at this end, and it's closed at that end. And what that means is that it could not have been carved out by classical rivers of water. They had nowhere to flow. So the question was, how did Hebe's Chasma form in the first place, and what might it teach us about the rest of the Mariner Valley network? Let's go back a slide there, Chris, please. Thank you. Now, planetary scientists who studied that European Space Agency image suggested in a scientific paper that Hebe's Chasma was initiated by material flowing down giant sinkholes in the floor of what is now part of the Mariner Valley system. And the number one sinkhole is actually right at the end of this internal plateau, right out there. Of course, this begs the further question about how the sinkholes formed in the first place. Sorry? No, let's go back to, there we go, we'll stay with that. And what they determined was, they suggested that it had to be that there were layers which were either able to melt under Martian surface conditions or dissolve. The thing that could melt would have been permafrost, but permafrost under Martian conditions doesn't have the physical strength to hold huge cliffs up, which are kilometers high like this, but salt does. So they suggested that what was actually happening was that there was water, groundwater in the system, which actually dissolved the salt, forming these sinkholes down which the non-salt material could then go to start to initiate this chasma. Well, there's a second 2009 European Space Agency image that we seem to have missed at the time. Maybe it's because they didn't actually advertise it. Let's go to the next one, please, Chris. Here's, next one, please. Thank you. And here's a label of the full extent of the Valley Marineris. Let's go to the next one. Thank you. This is the extent of the Hebe's Chasma image. Next one. And this is the extent of the second high-resolution image of the entire mid-segment of the Mariner Valley. And this was re-released by the European Space Agency at the end of October 2011, which is when I finally spotted it. Now, before we leave here, let's just do a little bit of terminology. For some reason or another, planetary geologists like using Latin words. So instead of just talking about canyons and chasms, they talk about chasma, for a single canyon, and chasmata, which is the plural. So if I use those terms, that's what I mean. Let's go to the next one, please, Chris. This is the image in question, showing you the topography of the chasmata that make up the Mariner Valley. There's Candor Chasma to the north. There's Coprates to the south. And then in here, you've got Melas, Ophir, and here up here, there's Hebe's Chasma. And these chasmata all cut into a very obvious flat-topped plateau. You can see the flat top of the plateau here, and you can see it through here. And that's made up of light-colored material. Now be aware that this image, just like the original image I talked to you about in 2010, this image has a 4 times vertical exaggeration, and that serves to highlight the many details of the slopes, but it means that the topography doesn't actually quite look like this if you were actually floating off in Martian orbit. Now, the original work on Hebe's Chasma came to my attention because scientists had already studied it and published their results. But for this, I've checked. I cannot find any science paper that gives ESA's interpretation, European Space Agency's interpretation of this image. So basically that means it's open for both interpretation, deciphering, and/or speculation. And you're going to get a lot of speculation tonight. So let's start by looking at the most obvious feature, the chasma walls. Next one, please, Chris. What I'll do, in order for you to know where you are in the system, each of these pictures will have an insert up here, a location insert of the overall image itself, with a little green box showing you where we are. So here we are at the eastern end of Coprates Chasma, and this nicely illustrates the nature of the erosional features that decorate the light-colored steep chasma walls. Now, at first glance, you might think they reflect complex geological structures in the rocks of the chasma walls. You might think they're folds or something like that. However, next one, please, Chris. This slide from the western end of Ophir Chasma shows that this is not so. Note the smooth chasma wall right here, where there's clearly been a relatively recent landslide that's wiped the wall clean. There's the landslide. And note the very simple horizontal layering that's revealed in the uppermost part of the cliff there. And you can actually see it down here very, very faintly, but that's where you can see it the most clearly. So this apparently complex herringbone structure on the rest of the chasma wall, which you can see over here, there's the herringbone structure. This is simply the expression of slow, progressive crumbling of the light-colored material that the chasma is cutting into here, which suggests to me, with my geological background, that the light-colored material is likely to be a thick pile of undisturbed layers of sandstone or volcanic ash. Next one, please, Chris. No, that's okay. Turning to the western end of Kandor Chasma, we can see the chasma head wall is retreating along 2 parallel trenches, here and here. Or can we? Is it? Let's have a closer look. First, look at the southern trench here. There's actually a link. There's a bridge going right across it. This trench here is not actually joined to the main chasma. And if you look at the northern trench here, it is clearly set well back from the head wall of the chasma itself. So what is going on here? Next one, please, Chris. This is even more striking down here. This is exactly the same kind of trench, but it's now clearly, very, very clearly isolated from both the other trenches and from the main chasma wall. Next, please. So here's the isolated trench. Look closely and you'll see a linear feature here along its southern edge, projecting out towards the right. And along it you'll see a sparsely populated chain of pits. There's one there, then again and again and again, and there they are again. And in fact there's also another feature here parallel to it with much, much smaller pits. Where did the material that originally filled the trench go? Like Hebe's Chasma, this trench is closed at both ends. It's closed at this end and it's closed at that end. Maybe the trench was dug by wind. But if you look here, the slump here on the south side clearly indicates that material is falling into the trench as opposed to being dug out of it. Next one, please, Chris. So I'm going to suggest that these are collapse features formed, as in the hypothesis for Hebe's Chasma, by the removal of material at depth which created sinkholes into which plateau material could collapse to form what I refer to as structurally controlled collapsed pits and trenches. As the pits and trenches link up, the chasma head wall retreats and the chasmata grow in length. And in fact, it's interesting to just look at this one up here. Here's an elliptical to circular pit, completely isolated from everything else, But the only way this could have formed here, again, is that it's some form of collapsed pit. And I think this gives some support to the hypothesis I'm putting in front of you. Next one, please, Chris. But what provides the structural control for these structurally controlled aligned trenches? To address that question, we need to move to the preserved plateau area between Coprates and Kandor chasmata. Now, superficially, these channels that you can see here, they look like a braided network of streams, but if you look closely, you'll see that many of them are segmented. Look here, for example. There we go, right there. Watch this. It comes as a segment and it kicks down, segment and kicks down, segment. There it is again, segment, and it kicks down and again. And in fact, you can see it all the way through the entire network. Those segments are uniformly misaligned with respect to the overall channel trend. As a geologist would instantly recognize these to be tectonic fractures, and a structural geologist, which is what I spent the last 40 years being, would recognize that they formed in response to right-handed sideways shearing. But look even more closely, and you'll see that many of these fractures, you can see it quite nicely up here, are actually rifts. Look there again. They're flat-bottomed, they've got nice parallel sides, and then there's like a keystone in the middle has dropped down, rather like the Ottawa Valley. Now, given how long and narrow these features are, coupled with the evidence for their origin as fractures, most geologists would interpret these as magmatic dikes, vertical sheets of magma injected into fractures. The magma, injected from underground, never quite got to the surface. And as it cooled and solidified, it shrank, just like anything that cools does, leaving a space between it and the plateau surface into which the material collapsed, forming the long, skinny, segmented rifts. Now, these segmented fractures and dikes had a significant role to play in determining where the walls of Kandor and Coprates chasmata would form. Next one, please, Chris.
Simon?
Yes?
Can you go back to that for a moment?
Yep.
Down in the left quadrant, all the minor craters there all have a dust trail or something down to the southwest.
Yep, okay, I see that, yep.
How do you explain that?
Oh, that's going to be a result of either oblique impact, or it's going to be a result of a northeast wind.
Okay.
Okay.
Yeah. Thank you.
Okay, good. So let's leave the plateau for a moment and look in the interior of the chasmata, starting with the western half of Kandor chasma, located here on the global image. Next one, please, Chris. What's the first thing you notice here? It's not as complicated as you think, the colors. The plateau material and the cliffs bounding the chasmata are light buff in color, but the floor of the chasma, and locally the lower parts of the cliff, there's the lower part of the cliff, but look at the floor through here, the floor here, and the floor through here. They're distinctly darker, and I would in fact call those colors medium gray to dark brown. Next one, please, Chris. Let's zero in on this area here that I've highlighted that is remarkably free of dust and rubble to see what the dark stuff really looks like. Next one, please. The material on the floor of the chasma here is very different in appearance from that in the plateau and the cliffs. The rock appears to be very smooth and homogeneous, and it's broken by short fractures that intersect each other at high angles. Look, there's a set of fractures which are oriented like this, and there's a set of fractures which are perpendicular to them, and you can see that pattern all the way through. You can even see it down here. But here, that grey material is actually overlain by a chocolate brown coloured material, quite distinct, with a very different fracture pattern. Look, these fractures here sort of form polygons rather than rectangular blocks. Now, I can't know for certain, because you've got to go there to actually ground truth this, but from where I stand, this sure looks to me like two sheets of dark magma, each of a different composition, likely similar to the basalts and other rocks that underlie the Earth's ocean floors. Next one, please, Chris. Now, before I try and draw all these threads together, I'd like to turn to further evidence for the processes that exploited the presence of initial fault systems to form the Valles Marineris that we actually see today. Now, here's the north wall of the eastern end of Coprites Chasma, where we can see two distinct stages of landslide formation. In the upper left here, there's a very clear landslide that's perched. It never actually managed to get all the way down to the valley floor, yet. It will one day. Just keep an eye on it. And to the right, over here, is a landslide that dropped to the valley floor, but was in part confronted by a buttress, a mountain range, if you will, in the floor of the valley, of high-standing rocks that it had to flow around. Next one, please. But landslides don't simply flow wherever they please. And in this example from Ophir Chasma, the landslide has been channeled to flow through here, between these two promontories, actually of resistant plateau material, on its way down to the chasma floor. While we're here, note the isolated collapse pit right here, clearly standing behind and disconnected from the chasma wall. I think that has to be a collapse pit. I can't think of any other way of explaining it. Next one, please. So, what happened to all that material that slid down the cliffs and onto the valley floor? Let's zero in on the floor of the western part of Condor Chasma and see. Next one, please. So here we see three different aspects of flow of landslide material on the chasma floor itself. At the top right over here, you can clearly see there's rubble that's basically still sitting at the foot of the cliff that it slid down. Here, over in this light color here, that occupies most of the frame is plateau material that has been reworked after the landslide that brought it down to the valley floor. In the right half of this light colored material, you can actually see a cliff right there. That's the top of the cliff. That's the cliff wall. This is the base of the cliff. You can see a cliff that has been eroded into this material after it reached the chasma floor. And these ill-defined, streaky, channel-like features look to me like that they represent surface streams, perhaps of water, that began redistributing that landslide material. Notice how the light-colored material laps on top of the grey rubble. And that would suggest that it's younger, that the grey landslide material is actually older. And thirdly, notice this medium brown material over here, this really smooth stuff over on the right-hand side. It's apparently smooth and featureless and looks to me as though it laps onto the light-colored material, which would make it the youngest deposit in this frame. If it is indeed a relatively young sediment, could it be a lake floor? The mud that actually forms on lake floors? I don't know. This is pure speculation on my part. You may say everything I've said up till now has been speculation, and perhaps it is. So, next one please, Chris. So how do all these detailed observations fit together? And what do they imply for the origin and development of the largest valley network in the solar system? Here's my take on deciphering this image. In part, it's inspired by the story proposed by those professional planetary geologists for Hebe's Chasma, located at the very top left here of the... Oh, what did I do? Thank you, Chris. Whatever I did, he recovered for me. Hebe's Chasma up here. So first, let's look at the big picture. Valles Marineris appears to be made of two layers that underlie its floor and its walls, respectively. I think that the valley floor approximates to the top of a layer of erosionally resistant magma. Geologically, we'd refer to it as basalt in the grey, and ultramafic material, if you know what that is, in the chocolate-coloured brown. This material could be in the form of lava flows that erupted onto the Martian surface, or it could be as horizontal sills, as they called, which were injected underground along the layering of pre-existing older rocks. The walls of the chasmata would seem to be made of horizontal deposits of either sandstone or volcanic ash. Now, the growth of the chasmata is clearly influenced by the process of structurally controlled collapse of material into initially isolated pits and trenches aligned along fault structures. These fault structures have also controlled the emplacement of more magma as vertical dikes, maybe similar to that which underlies the valley floor, and maybe not. Where does all this magma, lava, ash come from? Well, Tharsis Uplift at the western end of the Valles Marineris is the largest, most long-lived volcanic center in the solar system. We still know very little about it, so we can speculate all we want. Suppose that instead of the uplift of Tharsis initiating Valles Marineris, which has been suggested by many people, suppose it was the magmas or lavas flowing eastwards as horizontal and vertical sheets that predetermined the 3D structure of the valley network. Why would the structural control over the vertical dikes be related to right-hand shearing? I have no idea. But these are first-order observations. Where does the material go to allow formation of isolated, structurally controlled collapse pits and trenches during valley initiation? In Hebe's Chasma, as I pointed out, the professionals suggest that salt layers were locally dissolved to allow for the sinkholes to form, and that the silicate materials, the non-salt material, of the plateau went down the sinkholes. But we've just seen that the isolated collapsed trenches and pits here appear to be associated with segmented magmatic dikes, which, believe me, are not easily soluble. Now, I can only speculate, and you should beware of those who speculate. But is it conceivable that the dike magmas were drawn down vertically before they had cooled and crystallized by a drop in magmatic pressure, thereby leaving lots of space above them in structurally controlled collapse, underground collapse? I don't know, but these are the kinds of models, these are the kinds of ideas that will be uppermost in the minds of planetary geologists, the professionals that do start to interpret this image, or have already done so but haven't told us about it yet. So how did the initial chasmata evolve into a broad valley network? In addition to the growth and the coalescence of initially structurally controlled trenches, we've seen clear evidence for at least 3 processes that would widen and steepen the initial valley network. The first 2, instantaneous landslides plus slow ongoing crumbling of steep cliffs, combined to widen and lengthen the valley segments. The third involves various flow mechanisms to move material along the valley floor to empty and deepen the chasmata, including mass flow of landslide material, redistribution of that landslide material by streams and rivers, and processes possibly associated with localized lakes. Observation of the largest valley in the solar system, of how the largest valley in the solar system formed and evolved, is only just beginning. Is the story I've deciphered for you tonight valid? Who knows? It's going to require ground truthing to actually test that. Eventually, somebody will have to go there to see whether any of these hypotheses actually stand up to scrutiny. But my take-home message tonight is this. By releasing detailed images like this, the European Space Agency is allowing us all to participate, even at arm's length, in the deciphering of this story. Thanks for listening.
Just a couple of quick questions. So are you suggesting that it was subsurface flow, horizontal flow of magma that caused the undercutting that led to the collapse of these pits?
No, what I'm suggesting is that the erosion down through the possible sandstone and volcanic ash, that was easy. But once you get down to a layer of mafic magma, basaltic magma is strong stuff as far as erosion is concerned. That could have been older lavas, which flowed out over the surface, onto which volcanic ash or sand was deposited. Or the sand or volcanic ash, the light stuff, could be the older material. In that case, it could be a sheet or series of sheets of mafic magma which flowed out horizontally. That would define the floor of the mature valley. To define where the walls are, that would be related to vertical sheets of magma, which may or may not be the same magma as in the horizontal floor, because they could be later. So there are lots of variables and unknowns, but from this image, just looking at the textures, the structures, and the color differences, you can put together a story like this, which of course is a hypothesis, which requires testing.
Do the crater counts on the floor vis-a-vis the crater counts on the upper plateau give us any indication of the age of the actual valley formation?
That I'm uncertain of. However, since I haven't looked at it systematically, but given that you've got a process whereby even after the impacts in the plateau surface have occurred, you then eroded into that plateau, and you've got all of this active erosion and deposition going on in the valley floor, that would mean that in fact you didn't have a preserved record. And the fact that there's not much in the way of impact structures in the valley floor still doesn't enable us to then calibrate the age of the floor.
Simon,
Paul.
now that Mars Express has taken these photographs, you have a still photo now. You can from time to time check if there's any type of motion, could you not, with this type of magnification?
Yes, you could. But you know, Paul, I would very, very much doubt that there's been any significant volcanism along this segment of the Mariana Valley since about 3.8 billion years ago. However, when people are looking at the Olympus Mons, which is the largest volcano in the solar system, and it's just on the northwestern edge of the Tharsis uplift, if you just look at any of the Martian images, satellite images, the thing that strikes you is how smooth it is. There's very little in the way of impact structures on the top of this gigantic volcano. And the interpretation is that the surface volcanism, the lavas that covered the top of the volcano, are as young as 10 million years old, potentially. So it's not out of the question that some of this magmatism in the valley might be young, but I doubt it.
Simon, Mars's gravity is about a third of Earth's.
Mm-hmm.
What does that do for all the theories? Like, I mean, we can't compare Mars to Earth in terms of geological activity, can we?
But what that's going to do, that means, for example, that the response of rocks to gravity will be lessened.
Like a talus slope?
But you're still going to get them. It's just that maybe the size may vary.
They're more pronounced.
The actual velocity of material coming down a slope may vary. But remember, in this image, although those cliffs look like they're vertical, there's a 4 times a vertical exaggeration in the image. But it's a little bit like Mercury. If you look at Mercury and compare the surface of Mercury with the surface of the Moon, it turns out that the topography is much more subdued on Mercury than it is on the Moon. Why? Because Mercury actually, despite its small size, has a very large metal core, and therefore the gravity of Mercury is significant. And so it will have an impact on the precise details of the topography, but the actual processes that are occurring won't necessarily be affected.
What is the gravity on Mercury?
You have to ask one of the physicists in the audience. I'm just a simple geologist.
Half of Earth?
I don't know. I cannot tell you. Oh, no, sorry. I was actually reading quite recently that I believe actually it is comparable, but I can't support that.
Simon, I was wondering how deep these canyons are, say, compared to the...
They are kilometers deep. So when you see this impression of depth, it is real. If you were standing on the edge of the cliff, you better not have vertigo. I've been to the Grand Canyon. I got vertigo just standing on the car park, at the edge of the car park.
When interpreting an image, especially on such a large scale as that, would it not help to also have a contour map so you can see, which areas on the floor really do have the lowest elevations, relative to regions around them?
That, in fact, is what they did with Hebe's Chasma. And when they released the Hebe's Chasma image like this, they released the, what's the word for it? The digital elevation model. And so you could actually see in the digital elevation model that the sinkholes that they were proposing were actually, the big one at the very western end is actually 5 kilometers deeper than the average floor of Hebe's Chasma. But you're right. If they had also released the digital elevation model for this would have been an excellent cross-check. Gary.
Grand Canyon compared to, what would be the ratio of Grand Canyon to this height?
In terms of height, I don't know, but I can tell you this, that you know that at the very western end of the Mariana Valley, there's the Noctis, Labyrinthus Noctis, I think it's called, which looks like a labyrinth. It actually looks like a city plan of right-angled canyons. Well, the length of the Grand Canyon would fall into that.
Marineris is about the length of the United States.
It is. East-west, it actually will go from Los Angeles to New York. It is huge.
So the Grand Canyon's only 400 miles long, I think?
Something along those lines. If you're asking me for numbers, I often don't have them in my head. Geological processes I got at my fingertips. Thanks again.